We're almost done. Real gases. So we've been talking about ideal gases. Real gases behave like ideal gases under a wide range of conditions, but there are situations where they don't behave ideally. So an ideal gas has no attractions between gas particles, and the gas particles have negligible volume. So at STP, we see that if we calculate the molar volume of an ideal gas, it should be 22.41. And if we calculate the molar volumes of these real gases, very, very close. And in fact, helium is the same. But if we go to high pressures or low temperatures, they do not behave the same. And that's because real gases have a finite volume. So here, if we take this sample of gas and we compress it, so we're making the pressure higher. Now the molecules are taking up a larger volume, larger proportion of the total space than they were before. And if we continue to squish that, eventually we're going to condense it into a liquid. And now it's definitely not going to follow the ideal gas law. So the volume of the atoms here, this is argon, so they're not molecules. The volume of the molecules becomes more and more significant at higher and higher pressures. So here we're looking at the molar volume of a gas as a function of pressure. And we have a real gas, argon, and we have an ideal gas in the red here. And at low pressures, low meaning like under 200 atmospheres, which is like crazy high, way down here, they behave the same. But as we increase the pressure, the volume of the argon is going to be larger than what's predicted by the ideal gas law, because the ideal gas law doesn't take into account that the particles do actually have some volume, and so we see this deviation. Guyn and van der Waals modified the ideal gas equation to fit the behavior of real gases. This is called the van der Waals equation. And so to compensate for the volume changes, he added a term. So I just want you to have heard that this equation exists. We're not going to do anything with it. The other thing that happens is we have intermolecular attractions. So at high temperatures, the gases behave as the ideal gas law predicts. Gas particles at high temperatures have high kinetic energy, and so when they bounce into each other, they bounce off so quickly they don't have time to stick together. But real gas particles do have attractions for other gas particles. And when they collide more slowly, as like happens at lower temperature, there's a chance for that attraction to take effect and slow things down. And so we see that at lower temperatures, the actual pressure is less than predicted because the particles are sticking to each other a little bit. So here if we look at the pressure of the gas versus the temperature, this is for 1 mole of gas in 1 liter. An ideal gas is going to be this nice straight line from 0 with a slope of whatever that is. And for xenon, we see that at these low temperatures, which really are not that low, the pressure is less than predicted because the particles are kind of hanging out with each other a little bit too much. Van der Waals also modified the equation for this. Pressure is smaller, and so it's a subtracting term here. And so there's constants. Let's see, where are those? Here are the constants, the Van der Waals constants. And these constants are different for different gases. And so you can put them all together and you get this mess. So I think what we can take away from that is the ideal gas law looks pretty nice in comparison to that. Yeah.
there's no actual ideal gases. It's not like
Right.
these are ideal gases and these are
Yeah.
gases.
The ideal gas is a gas that behaves in the way described by the ideal gas law and by kinetic molecular theory, that the size of the particles is negligible, the collisions are all elastic, and that. No real gas is an ideal gas, because just like with regular life, I mean, there's this ideal, but nothing ever matches up. Right?
Okay, so it's
Nothing's
just
perfect.
like close enough for us.
Yeah.
Right.
Under a wide range of conditions, real gases behave very similarly to ideal gas, and so the difference is not important at all, and so we can use that equation. It's nice and simple and great. Now, if you're dealing with very low temperatures or very high pressures, then you have to be concerned about the differences, and so there are other ways to compensate for that, but thankfully we don't have to do that. We can plot PV over RT versus pressure for 1 mole of a gas, and for an ideal gas, we would expect a horizontal line. And so we see there's a variety of deviations here. When the line goes above what's predicted, that means that the most important factor for that gas is its molar volume, and for things that go below, the most important factor is intermolecular attractions.